Welcome to optimization problem, new optimization problem. And I believe all of this is in your notes already, right? So a lot is already in there. All right, so what dimensions for a 1 liter cylindrical can will use the least amount of material? All right, so there is our diagram. Ooh, it's very pretty, right? We're looking at the amount of material, so that is surface area. Right, so there's 3 essential surfaces, right, to a cylinder. There are the 2 bases, and then there's that lateral area. Right? So we're going to write a primary equation for the quantity to be maximized. In this case, we are minimizing. So maximizing, minimizing, it's minimizing. We want to use the least amount of material. Right? We want to be able to hold a liter, but we want to spend the least as possible on the packing material. Otherwise, we have to charge more. So we can minimize the material by minimizing the surface area. Right? So area of a cylinder is 2 pi r squared. There's 2 circles plus 2 pi r h, the lateral area. And that's just simply circumference times the height of the cylinder. Okay. Now you see we have too many variables. Right? So we're going to write a secondary equation that can be used. You always have too many variables. Let's just put it that way. Write a secondary equation that can be used to change the primary equation to a single variable. The problem is not the a, right? It's because we're going to maximize or minimize, a. The problem is that there's an r and an h. And the one to get rid of course, is the h. Right, so write a secondary equation that can be used to change the primary equation to a single variable. This reduces the primary equation to one having a single independent variable. Right? We want one independent variable. We know we're going to have a dependent, that's okay. It's the independent. Right? So, and it's also our constraint. Our constraint is you have to be able to hold a liter. Right? Now, a liter is a measure of volume. It has nothing to do with it's nothing we can use for surface area. We need to change that into something that will work with the values for the radius and the height, and that is to change liters to centimeters. Right? So a liter is the same as 1,000 centimeters cubed. It'd be good to know that. It's probably the only conversion you ever really have to know. Right? So we're going to change that 1 liter to 1,000 centimeters cubed. So 1,000 equals pi r squared h. And of course, if we just simply divide by pi r squared, we have a way to replace h. So h is equal to 1,000 divided by pi r squared. So now we can go back to that primary equation and we're going to replace the h. So we have a equals 2 pi r squared plus 2 pi r times 1,000 divided by pi r squared. Right? And now we should just simplify that. So a equals 2 pi r squared plus, in the numerator that would be 2,000. In the denominator, the pi's cancel, one of the r's cancels, so 2,000 divided by r. Right? On the next page, because all this writing took up a lot of space, we are going to take the derivative. Yep. All right, so the limits on possible values here, r of course has got to be greater than 0. That's the one limit. Right? We don't know. I don't know how big r can be, but I know it can't be negative and it can't be 0. Right? Otherwise, I don't have any surface area at all. We're going to differentiate the equation and then solve for the critical values. All right. So I have rewritten that 2,000 divided by r using a negative exponent, right? So we can use the power rule. All right. So we have. And I'm going to write this as a of r, just because I like writing, at least for explaining, it's easy. It seems easier for me to write, have one consistent variable. So I can write a of r, a prime of r, a double prime of r. All right. So we have a prime of r equals, all right, so we take the derivative of 2 pi r squared, and that's going to be 4 pi r. Okay, and then this would be minus 2,000 r to the negative 2 power. All right, there we go. So we're going to test the primary equation for all critical points and endpoints and determine the desired maximum, in this case, minimum values depending on the situation. All right, so when you're not really sure of your endpoints, then we can always use a sign chart. Right? So extreme value tests when you're testing your endpoints, your critical points and endpoints. When you have a well-defined domain, when you're given like a table and you know it can only go from 1 to 100, right? You've got 1, you've got 100, you've got your critical points. It works out great. When you don't really have that well-defined domain, well, I could plug 0 in. Right? Yes, the minimum radius I can have is 0, and then I just have a piece of sheet metal. I don't even have a cylinder anymore, right? When you don't have that well-defined domain, it makes more sense to use a sign chart. So let's use a sign chart here. And before we can use a sign chart, we have to finish solving. So 0, let me put it over here actually, because I'm going to run out of space. 0 equals 4 pi r minus 2,000. I am going to change that to divided by r squared. That'll make a lot more sense. I can cross multiply. We're going to add 2,000 divided by r squared to both sides. So we have 2,000 divided by r squared equals 4 pi r. Now you can reduce within a fraction, across a numerator, or across a denominator. Don't reduce out variables, but you can certainly reduce out coefficients. Right, so if we divide both of those by 4, that just becomes pi r, and this becomes 500. All right, just saves us the trouble of reducing later. So we have 500 equals pi r cubed. All right, we'll divide both sides by pi. I'm thinking, where do I fit this? I don't have a whole lot of space here. So let me fit this right over here. Boop, 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 boop. Continuing over here. All right, so I'm going to divide by pi, and I'm going to take the cube root. So r is equal to the cube root of 500 divided by pi. All right, there is our r. And you can leave it like that. You don't have to rationalize it. It's fine. All right, just make sure it's clear and that it's clear that it's the cube root of 500 divided by pi. All right. So now we're going to test the primary equation for all. We're going to test we're going to use a sign chart, right, to check to see if this is a relative max or relative min. All right. So we got 0 down. Any day now. Any day now. There we go. 500 divided by pi. All right, so that's our critical point. I have no idea. I can take a handy dandy calculator and take 500 divided by pi and then raise that to the 1/3 power. And that is approximately 5 point. So I'm going to just put that underneath that. I'll need that for later anyway. 5.4193. Use at least 4 decimal places. All right. You can include, if I want to be even more accurate, I can include more. I'll include 5. 2, 6. The one after that is 0. All right. So something less than. How about 1? 1 is less. Something more. How about 6? All right, and we're going to plug that into the derivative. All right, so we have, if I plug in, and I'm going to use the one where I simplified the r squared. All right, so ignore the 0 there. All right, so plug in the 1. I've got 4 pi minus, well, if I put 1 in the denominator, I've got 4 pi minus 2,000. Now, I don't know exactly how much that is, but I know 2,000 is a lot more than 4 pi. Right? 4 pi is like 12 or 13, 14, something like that. Right? 2,000 is a lot more than that. This is clearly going to be negative, without a doubt. All right, so now if I plug in 6, I've got 24 pi minus whatever 2,000 divided by 36 is. Let's just make sure that's a positive number there, or negative number, or whatever it may be. All right, so 24 pi is 75.3982. And if I take 2,000 and divide that by 36, I get only 55.55555, lots of fives. So that's going to be a positive number. All right, so let's write my sentence there. So R equals the cube root of 500 divided by pi is a relative min, because, I'm going to use a symbol here, because a prime of R changes signs from negative to positive at, oh, I need one more line of space. It can move down just a little bit. I don't need a whole lot of space for 7 and 8. Come on, just go down. There we go. At R equals the cube root of 500 divided by pi. There we go. All right, nice, simple, short, right to the point. I'm going to move my sign chart over just a tad, if I can. Can that part move over? Oh, there goes that part. Just so I'm not blocking my writing there. There we go. All right, take the second derivative to check our answer. All right, so the second derivative, we want to go back to the one where it was written as a negative exponent. A double prime of R equals, so this would be 4 pi. Minus, and then, actually now that would be plus, because I would have negative 2 times negative 2,000, so that would be 4,000 R cubed. All right, well, I don't know exactly what that number is, but that is definitely greater than 0, right? There's no way, because I've got 4 pi and I'm adding a positive number, right? So that is definitely greater than 0, right? So since a double prime of the cube root of 500 divided by pi is greater than 0, A of R is concave up at R equals the cube root of 500 divided by pi, and R equals the cube root of 500 divided by pi is a relative min. Maybe I should put N there for. Would that make a better sentence? There. Love these symbols. All right, now we just need to solve for the other variables needed to answer the question. We're done answering the question. We've found our critical point. We verified. I no longer remember the question, but that's okay. We just go right back to the beginning. And it says, what dimensions will use the least amount of material? So we have the radius. We need the height. And we should use this equation right there to find our other variable. So 1,000 divided by pi r squared. All right, so the material is minimized when r equals the cube root of 500 divided by pi, and, or maybe we should put radius. Let's put radius of the can. Let's be really specific. When the radius of the can is the cube root. There's no reason we have to go to a decimal equivalent. We could, but let's just use the exact answer, 500, the cube root of 500 pi. And the height is, oh, we should put units on that. That was centimeters. And the height is, so it was 1,000 divided by pi r squared. So pi cube root, oh, I need just an inch more space. Cube root of 500 divided by pi, right? All squared. There we go. And that's centimeters. Right? No reason we have to simplify that out further. That is totally fine. All right? And so we have solved this problem. We have used calculus to find the correct radius and height to minimize the material and minimize the costs. Right? And let me see if it asks to minimize, it just has to minimize the material, right? Yes, least amount of material. So we have answered the question that we needed to answer, and that's the end of this podcast. Thanks for watching. Bye for now.